Hi everyone, Sin here. Today we're going to do some engineering and stuff, and I'm going to show you how to interface your Arduino with LabVIEW. Before we get started, we require the following items: an Arduino Uno Mega or etc., LabVIEW 2011 and greater, the latest NI Visa drivers for your version of LabVIEW, the JKI VI Package Manager, the LINX add-on, and lastly the Arduino drivers and IDE. Firstly, let's open the VI Package Manager, which is a nice utility for downloading various LabVIEW add-ons. Next, we want to go to the search bar and type in Arduino. Once our results have appeared, we want to select and install the LINX add-on. Notice, however, there is also a LabVIEW interface for Arduino add-on. This is no longer supported by NI and has been superseded by LINX. Now let's install the LINX add-on. Once the package loads, you want to click on the install button for your version of LabVIEW. As you can see, I've pre-installed this so we can move on to the next step. Now let's confirm that the Arduino and PC are communicating properly. To do this, let's open NI Max. First, let's confirm if we have the latest NI Visa driver installed. Click and expand software and go down and select your NI Visa driver and confirm it's the latest version for your version of LabVIEW. Next, we want to go to Devices and Interfaces up here and expand. Now select the COM port your Arduino is currently connected to. For my PC, it's COM port 6. If you look under the port description, you can see that the Arduino Uno is listed. You can also see and adjust various other port settings such as the baud rate, which may be important to you depending on your application. You can also see these details in your PC's device manager, which I will not cover here. Now, a quick way to test if your Visa session is active is to use the Visa test panel. If you open that here, you will get a nice test panel which will show you again your serial port settings. Select input and output and do a quick write. If you get no error on return, it means your Arduino is communicating correctly. An additional method to confirm your Arduino is communicating with your PC is to open the Arduino IDE. Once loaded, you will have a basic sketch open. Go to Tools and select Port. Again, you can see COM port 6 confirms the Arduino is present. You can also select Board Info, which confirms you are able to communicate with your Arduino. As if you couldn't, an error would occur when selected. Now that communications are confirmed, let's open LabVIEW to load the LINX firmware onto the Arduino. Go to Tools, select Maker Hub, LINX, LINX Firmware Wizard. Once loaded, select the device family, Arduino, device type, Uno in my case, the firmware method, USB, click Next, select the COM port, COM6 in my case, and then confirm the firmware version and upload type, and then select Next. Now we wait for the firmware to upload to the Arduino. Now that the firmware has been uploaded, we can begin programming the Arduino in LabVIEW. So let's begin. Alright, now that we've loaded the firmware onto the Arduino, a good place to start with hardware I find is to build off an existing example. Generally, when you purchase hardware, it will come with an example whether it's in C, Python or MATLAB, etc. A good starting point is to replicate those examples in LabVIEW to confirm that you have the same functionality. All I'm going to do is demonstrate how I built off the Blink sketch example from the Arduino IDE on the left and develop this functionality in LabVIEW with the LINX functions. On the right, you can see the VI front panel I've prepared, which shows the indicators and circuit schematic for the LED connected to the Arduino. In short, what are we doing? We are turning on and off the LED at a frequency of 1 Hz. In the sketch code, we can see we are writing to the digital input and output pin 13 a high or a low value every second. What does this do? When high, 5 volts is outputted on pin 13 and the LED turns on. When low, 0 volts is outputted on pin 13 and the LED turns off. In LabVIEW, we are replicating this function by writing to pin 13 on the Arduino at a frequency we select on the slider control here. Okay, now that we have a basic theory of operation, let's look at the block diagram to understand how we are programming the Arduino. The first place we're going to start when we create a new VI is to actually locate the LINX functions under the menu Maker Hub, LINX. Let's pin this so we can see it at all times. As you can see here, there are a few basic and essential functions, open and close. You need to open your Visa session to your hardware, whether it's an Arduino, a Raspberry Pi or anything else supported by the LINX toolkit. And then you need to close that session to exit it properly. If we look at the left of the block diagram here, we're opening a Visa session to the Arduino. allocating the resources in memory and configuring any serial parameters. In this case, we're only specifying the serial address, which is COM6, as we determined previously. All other configuration settings are set to their default values, such as the baud rate, for example. As you can see, this is a polymorphic VI, which allows different configurations of communication protocols. Let's leave this as automatic. Once we have configured the OpenVI, let's read its output terminal to confirm we're communicating with the Arduino successfully in LabVIEW. This will be the third and final method confirming we are talking to the Arduino. It's always a good idea to do a bit of due diligence. If we select the OpenVI and look at the context hub, we can see an output listed as device name. This will show a string confirming what model Arduino is connected. Now let's place a breakpoint here to stop the code and look at the output by placing a probe. We can now examine the output as the code runs and should see the string output in the probe display and the string indicator on the front panel. So let's run the code, wait for it to upload to the Arduino. Once we reach the breakpoint, the code will pause, and we can see we've successfully read the device name in both the probe display and the string indicator. Now that we know the code is running, let's abort it and see what happens if you don't close the visa session properly. A common error most people make when interfacing with hardware. So we abort, we remove the breakpoint by breakpoint clear. Let's leave this probe open to see what happens. Now let's run this VI. And as we can see, it failed to connect to the Arduino. The reason being, we did not appropriately close the resource allocated to COM port 6. Now if we continue, this will be flushed from memory and we can run the code successfully again. Let's run. And now we can see we're connected to the Arduino, as we've now freed up that resource. If we click stop, the resource will close and we will not have that issue again. Again, we run the code and we have a blinking LED and let's stop the code. So let's remember, it's always important to close your resources appropriately and not to prematurely abort them. You always want to handle this using the appropriate error handling methods in your VI. The way we're handling errors in this VI is very simple. Once the loop stops by either having an error occur or the stop function becoming true, we exit. The close function then frees any resources and closes the session to the hardware, in this case the Arduino. Then any resulting errors are handled by this error function. If we go to Context Hub by clicking this question mark here, we can see a short description of what this VI does. The simple error handler VI will just return a description of the error once it occurs. This is very handy when you're developing your VIs and you just need a simple error return. You can access the simple error handling VI by simply right-clicking the block diagram, going to dialog and user interface, and then finding the simple error handler. Additionally, you can click Control and spacebar to bring up the quick drop menu and type in simple error handler. Double click and the error handling VI will appear. Now that we know how to open and close the sessions properly to our hardware, let's look at the meat of the code to see how we're actually writing to pin 13, flashing the LED, and handling the frequency. First, let's organize our workspace so we have a clearer picture. We'll close the probe. Yes. Now essentially there are 4 sections to our while loop. The first being the frequency control, which determines the loop speed. The second being a simple piece of logic to determine if the LED will be on and off. The third, actually writing the Boolean value to the appropriate pin, which is pin 13. And the fourth is the loop condition, so determining when to stop the while loop. Let's start by examining the frequency control section of the while loop. First, we're taking an integer value and taking its reciprocal. We're multiplying this value by 1000 to convert it to milliseconds. We are then converting it to an unsigned 32-bit integer, and then feeding this value into the wait milliseconds function, which will hold the loop for the specified amount of milliseconds before iterating to the next loop. This way, we're able to control the frequency of the while loop and hence the frequency of the LED flashing on the Arduino. You may notice on the front panel, the frequency control is a horizontal slide. You can access this horizontal slide by right-clicking the front panel, going to numeric, and then horizontal pointer slide. Notice the values are only from 1 to 10. This is being done by right-clicking the control, properties, data entry, minimum value set to 1, maximum value set to 10, and the increment set to 1. Notice that the properties are coerced and nearest. This allows you to increment in integer values. If we go back to the frequency section of the code, You may have been asking yourself, why did I convert the double value of the frequency into an unsigned 32-bit integer? The reason is, it's generally good practice to convert different data representations when you have two different types between functions. This is to avoid coercion dots, which I will not go into detail here. Now let's look at the digital write function from the LINX library. This is quite a simple function. It simply allows you to select a channel and write a boolean value to that digital channel. In this case, we're only writing to a single channel. As you can see, this is again a polymorphic VI, and we have selected one channel. You are able to also select n channels or automatic. If you select n channels, it will accept an array as an input, which will specify the range of channels you want to write to. It will also require an array of boolean inputs. Let's go back to automatic. And as you can see, it has gone back to single channel, channel 13, and we are writing the boolean value, which we determine here. Now it's easy to manually control the LED by simply placing a boolean control which you can turn on and off. But in our case, I want to completely replicate the example blink sketch by having this LED turn on and off with the frequency of the while loop. To handle this in this video, all I'm doing is implementing a case structure which will write a true value or a false value depending on if the loop counter is odd or even. How is this done? I take the loop counter value, divide it by 2, and check if the remainder is 0 or not. If the remainder is 0, we have an even value and we write true. If the remainder is not 0, we have an odd value and we write false. This will illuminate the LED and write to the digital output pin of the Arduino. Lastly, what's the loop condition of the while loop? It's if an error occurs or we press the stop button. It then simply exits, closes the session, handles any errors. Now that we have a basic understanding of how we're blinking an LED at a frequency of 1 second or at a rate we select, let's see how this works in real time with the Arduino. The code is now running, and as we can see, the LED on the VI and in our circuit are blinking in sync. As we adjust the slider between 1 and 10 Hz, we see the LED flashing with the appropriate frequency as we expected. Thank you for watching my video. Please subscribe, share and comment if you enjoyed or didn't below. See you next time.